Good morning, dear students. My name is Ferhan Mazher, and today is 8th of September 2021. Right now, I am with the 11th Cambridge class, and today we have set our hearts to solve MCQ paper. The subject we are studying is Physics 5054. The paper we are attempting is Summer 2005. We call it May June 2005. In the A part of this lesson, we have already done up till from question number 1 till question number 27. In this session, we are going to start from question number 28 and we will go up to question number 40. So it's an MCQ paper. The question number 28 is showing up on your screen. A cell is connected in series with an ammeter and a lamp. The current is 1 ampere. So here you can see in the diagram, there is a cell, a single cell, and there is a single lamp in the circuit. The ammeter is telling you how much current is coming out of the battery. And he says that it gives you a value of 1 ampere. So the current coming out of the battery is 1 ampere. In which circuit using identical cells, lamps, and ammeters is the current reading 2 ampere? So the current coming out of the battery is 1 ampere. Now he wants us that the current should be 2 ampere. How the current will become 2 ampere? If you know the current coming from the battery, the formula is very simple. Let me show you here. The current coming from the battery, the formula is the current coming from the battery, the formula is I is equals to EMF divided by the resistance, the total resistance of the circuit. Now you want the current to become double. The current can be doubled with the same cell if the resistance becomes half, the total resistance of the circuit becomes half. Okay, the current will become double if the total resistance of the circuit will become half. So now I am looking for that option where the battery is same, but the resistance has become half. Now, how you can make the resistance half? By connecting two identical lamps parallel to each other. You must have studied, we have completed that chapter, that when you connect the lamps parallel to each other, the combined resistance will become half. If you have two cells, you connect them in parallel to each other, the combined resistance or the equivalent resistance or their combined effect will be that the resistance will become half. If you connect the two identical lamps in series with each other, then the combined resistance will become double as compared to a single lamp. Okay, so we are looking for that option where the lamps are connected in parallel to each other and a single cell is connected. So that will be the D choice. That will be the D choice. Okay, so that will be the D choice. Why not we use this one? Because here you have doubled the EMF. If you double the EMF, if you use two cells, the EMF becomes double. Even then the current can also be doubled. But the problem with the diagram B is here the resistance has also become double. Okay, so when in the B option, that cannot be the option. The reason is you doubled the EMF, but you have also doubled the resistance. So the current still will be 1 ampere. In the A option, the A is not the answer. Why? Because you use two cells, but both the cells are connected in parallel to each other. You know, when you connect the cells in parallel to each other, their EMF do not increase. The combined EMF is still equals to the EMF of a single cell. So D is the right option. Question number 28. D is the right option. Let's check the answer. Question number 28. D is the right option, sir. Do you understand?
Yes, sir.
Okay. So here we are on the question number 29, and he says, which circuit contains a cell, a light emitting diode, and a fixed resistor? Which circuit contains a cell, a light emitting diode, and a fixed resistor? Okay, so look at the first diagram. In the first diagram, this is the cell, this is the fixed resistor, and this is the light emitting diode. Most probably, this is the answer. B, this is the cell, this is the fixed resistor. This is the light dependent resistor, LDR. This is not LED. There are two words, two different words I'm saying. We are looking for LED, light emitting diode. A is the right answer. This B diagram, this component, this is not LED. This is called LDR, light dependent resistor. Its resistance depends upon the intensity of light. So this is not the answer. This is not the answer. This is not the answer. Okay. So we were looking for that circuit in which we have a fixed resistor, we have a LED, light emitting diode, and a cell. So A is the right answer. Let me check the answer. Question number 29, A is the right answer, sir. Ji, Ahmad, do you understand?
Yes, sir.
Okay, shabash, shabash, shabash. You should always remember the difference between these two. This is light emitting diode, and this is light dependent resistor. This is called LED, and this is called LDR.
LDR.
Yeah. Okay.
Yes, sir.
So that was question number 29. Question number 30. In each of the circuit below, a short circuit occurs. In which circuit would the fuse blow and make the circuit safe to repair? You see, the fuse. Remember this thing: the fuse, the switch, and the circuit breaker. They all should be connected in the live wire. They all should be connected in the live wire. Okay.
Okay, sir.
So here the live wire is coming, the fuse is in the live wire. The short circuit happened after the fuse. So this is a good thing. Okay, this is a good thing, because here when the fuse will blow, your whole thing will be cut off from the live current. Here the fuse is in the live wire, but the problem is the short circuit happened here. So even the fuse blows, you will be still connected with the live. Here the fuse is connected in the neutral, which is totally wrong. Here the fuse is connected in the neutral wire, which is totally wrong. It should come before the lamp. Okay. So A looks the right answer. The fuse must be always connected in the live wire. So question number was 30. Question number 30. The choice is A. The choice is A. Next question. Question. You just try to understand what I'm saying. Okay. An alternating current is passed through a wire stretched between the poles of a magnet. Which way will the wire move? Okay. So remember this thing. Okay. Whenever you place a conductor which has current in it, whenever you place a wire which has current in it in a magnetic field, the the conductor will experience a force. And in our course, we always place the conductor perpendicular to the magnetic field. So the magnetic field is flowing from north to south. They are going from north to south, and the current is alternating current. So one time the current will flow towards me, and then towards the away from me. And whenever you place a conductor inside a magnetic field, the conductor is placed in such a way that it is perpendicular to the magnetic field. The conductor will move perpendicular to the magnetic field. We can tell the direction of that movement. Either we use the left hand rule. The rule is very simple. We use the left hand rule. The rule is you take your left hand like this. This is my left hand, and you stretch its three fingers. This thumb, this finger, and this finger. You see, it's very important to understand the this finger. This is my thumb. This is this finger. This is with my palm, and this finger is perpendicular to the palm. Okay, now you see they are mutually perpendicular to each other. You can see they are mutually perpendicular to each other. Very important. Okay, so you can see that. You can see that. Yeah, you can see that. So this is called F, M, and C. F means the force, M means the magnetic field, C means the current. For example, if I apply here, for example, the current is coming towards me, the magnetic field is flowing from north. This, you see, the current is coming towards me, the magnetic field is from north to south. My thumb will be pointing upward. So this will move upward. And when the direction of the current will reverse, because you have connected the alternating current direction always changes. So when the current is flowing towards me, the force will be experienced in upward direction, and when the current will flow away from me, then the force will be downward. So the wire will move up and down. The wire will move up and down. A little tricky for you because you have not yet studied this chapter, but in the next lesson we will study this thing. So question number 31, C looks the right answer, sir. Question number 31, C is the right answer. So here we have applied the left hand rule, and the left hand rule is about a conductor placed inside a magnetic field. It will experience a force. By using the left hand rule, I am able to tell in which direction that conductor will move. So question number 31C is the choice. Let's check the marking scheme. Question number 31C is the choice. Okay, so next question is this we have already studied. X and Y are wires carrying electric current at right angle to the page. P, Q, and R are plotting compasses. Any effect of the Earth's magnetic field has been ignored. So, what is true about the direction and the size of the currents? You see, whenever you have a current in a wire, around it a magnetic field is induced automatically. Naturally, this happens whenever there is a current flowing in a conductor. Around that, a magnetic field is created. That magnetic field is circular, and for example, here a wire X and wire Y has been shown. The wire X is represented with the dot. You know, that dot means that the current is coming out of the page. The current is coming out of the screen towards you. The Y wire also has been represented with the dot. And that means that the current is coming towards you. It is coming out of the screen or out of the page. It's coming towards you. That is, this dot represents the direction of the current in that conductor. So there are two conductors, X and Y. So around them we will have magnetic field. I told you that it's natural that whenever a current is flowing in a conductor, around it a magnetic field is created. That magnetic field is circular, and we can tell the direction of that magnetic field. Okay, we use the right hand rule. So the rule is very simple. What you do, you take your right hand. This is my right hand. You take your right hand. For example, if this represents the conductor, and through it the current is flowing upward, so I will hold it in my right hand in such a way. I will hold it in my right hand in such a way that my thumb is in the direction of the conventional current. My thumb is in the direction of the conventional current. Then, you know, the curls of my fingers, the curls of my fingers, they will be telling me the direction of the magnetic field. So if the current, for example, the current is coming out of the screen, so I will hold the conductor in this way, and My thumb is pointing towards me. This is my right hand. So it means that the magnetic field around it will be anti-clockwise. By using the right hand rule, I am able to tell what will be the direction of the magnetic field around that conductor. So if the current is coming out of the screen towards me, if the current is coming out of the screen towards me, I will hold it in my right hand in such a way, in my thumb, like this. My thumb is in the direction of the conventional current. The curls of my finger, they represents the magnetic field. So magnetic field will be anti-clockwise around that conductor. So it will be magnetic field will be around the x will be anti-clockwise. Magnetic field around the y will be also anti-clockwise. So that the whenever you place a magnetic compass near a whenever you place a magnetic compass near anywhere and any position, the alignment of the magnetic compass tells you the direction of the magnetic field. So you see at the point X, the magnetic near the X, the magnetic compass P is telling you the direction of the magnetic field is towards the top of the page. At the Y, near the Y, the magnetic compass R is telling you that the direction of the magnetic field is towards the bottom of the page. So in the middle, the compass Q is following X. The compass Q needle is following the magnetic lines of the X. Compass Q is following the magnetic lines produced by the X. It is not following the magnetic lines produced by the Y. So it means the magnetic field of X is very strong. It means that the current flowing in the X is larger than the current flowing in Y. So the direction of the current in both of them, they both were represented with the dots. It means that the current is coming out of the page. So X and Y, the direction of the current is the same, but the size of the current in the X is larger in as compared to the Y. So I think A is the choice. I think A is the choice. Question number 32. A is the choice. It looks to me A is the right choice. Let me first of all check. 32. A is the choice. Do you understand, Ahmed?
Yes, sir, I do.
Okay, here we go. Is the next question 33. A girl turns the handle of a small AC generator 4 times each second. The generator produces a maximum output voltage of 5 volt. Which of the following graphs best show this? Okay. Now, in uh, in 1 second, in 1 second, she turns the handle 5 times. Sorry, 4 times. Sorry. In 1 second, the girl is turning the handle 4 times. So in 1 second, 4 waves should be shown on the diagram. The voltage is 5 volt. So the amplitude should be 5. The amplitude should be 5. Positive 5 and negative 5. And in 1 second, there should be 5 waves. Let me check. So 1 wave, 2 wave, 3 waves, 4 waves. You see in the option A, in 1 second there are 4 waves because she did 4 revolutions in 1 second. So there should be 4 waves in 1 second there, and the amplitude should be 0.5 volt. So from mean position it should go 0.5 volt up and 0.5 volt below the mean position. So A is the right choice. Why this is not the right choice? You see, the volt is right. The maximum volt is 0.5 volt. But in 1 second, there are only 2 waves. That's wrong. She was doing 4 revolutions in 1 second. So there should be 4 waves in 1 second. So B is wrong. Why the C is wrong? It is showing 1, 2, 3, 4. The C is showing 4 waves in 1 second, but its amplitude is 0.25 volt, which is wrong. The maximum voltage was 0.5 volt. So C is also wrong. D is wrong because it's showing 0.25 volt. That's wrong because the voltage was 0.5 volt. It's showing 0.25 volt. That's why it's wrong. So B, C, D, they all are wrong. Only the A choice is the right choice. So question number 33, A is the right choice. Let's check. Question number 33, A is the right choice. Ahmad, do you understand this? This logic which we were
Yes,
talking
sir,
about?
I do.
Okay. So question number 33, A is the right choice. So we on your screen, question number 34 is showing up. Which statement about the action of a transformer is correct? The transformer is basically used to step up the voltage or step down the voltage. Okay, that's the basic function. You must have seen your transformers in your street, and they are transformers. You have seen transformers? Have you seen the transformers?
Yes, sir.
Okay, so the transformer's basic function is that it converts low voltage and convert it into high voltage, and it can also do another thing. It can take high voltage and convert it into low voltage. For example, the transformer which is in our street, it is converting 4000 volt into 220 volt, so that it can be fed to our homes. The electricity can be fed. So it can reduce the voltage. We call it step down transformer. It can increase the voltage. We call it step up transformers. So an EMF is induced in the secondary coil when an alternating voltage is applied to the primary coil. That is the working principle of the. It has two coils, primary coil and a secondary coil. In the primary coil we provide alternating current, and in the secondary coil automatically an EMF is induced. That's the working principle of the transformer. So A can be the choice. An EMF is induced in the secondary coil when there is a steady direct current. No, in the transformer we do not use the DC current. Direct current is not used. The current in the secondary coil is always larger than the current in the primary coil. That is not the case. The current might be larger than the current in the primary coil. The current might be smaller or less than the current in the primary coil. The voltage in the secondary coil is always larger than the voltage in the primary coil. No, the voltage output might be more than the voltage input. The voltage output might be less than the voltage input, because the transformers are can work two ways. It can either increase the voltage and it can also decrease the voltage. So A is the choice. Question number 34, A is the choice. Let me check the answer. Question number 34, A is the right choice, sir. Okay, so we are going to question number 35. Electric energy is transmitted at high alternating voltages. What is not a valid reason for doing this? You see, when the electricity is produced in a power station and then it is sent to the consumer, so that is sent by the transmission line. You must have seen big pylons, big towers, and big wires coming from Tarbela Dam towards Sargoda. So the electric energy is being transmitted and the voltage is kept very, very high. We keep the voltage very high because when we keep the voltage very high, the energy loss or the power loss in the transmission line reduces. If we keep the voltage high, for example, we make it 120,000 volt, then the power loss or the energy loss in the transmission line reduces. That is why we. His question is, what is not a valid reason for doing this? At high voltage, AC is a safer than DC. That is totally wrong thing. At high voltage, AC is safer than the DC. That is a wrong statement. So clearly, this is the answer. We are looking for that, which is not a valid reason. For a given power, there is a lower current with the high voltage. That's true. There is a smaller power loss at higher voltage and lower current. That is also true. The transmission lines can be thinner with the lower current. That is also true. We were looking for not a valid reason. So A is the right choice. Question number, let me check, 35. 35 is A is the choice. Okay, that's good. Question number 36, he says the diagram shows some of the important parts of a tube of a cathode ray oscilloscope. Which change in the voltage results in the position of the spot on the screen moving towards the top? You see, in the CRO, we have here, these are called Y plates. These are called Y plates. Here, a beam of electron is traveling towards the screen, and the beam of electron is negatively charged. If this upper plate will become positive, if this upper plate will become positive, what will happen? This beam of electrons will be attracted towards it. So on the screen, the beam of electron will move upward. If the lower plate will become positive, then the beam of electron will be deflected downward, and on the screen they will move towards the bottom. So which change in the voltage results in the position of the spot on the screen moving towards the top? V3. V3 should increase. If you make V3 more stronger, more positive, more, if the V3 is more and more positive, electrons are negative, so they will be attracted towards it, so they will be deflected upward. So on the screen, the electrons will go towards the top. So I think D is the choice. Question number 36, D is the choice. Let's check the answer first of all. Question number 36, D is the right choice, sir. Do you understand this? Cathode ray oscilloscope.
सर ये आप रिपीट कर देंगे?
You see, he's asking us to look for something by which I can move this beam of electron towards the top of this screen. Here is that screen. Here is that screen. So this beam of electron will go up if this upper plate, we call it Y plate, that becomes more and more positive. Because it will become positive, these electrons, they are negatively charged. They are naturally attracted to this positive plate. So they will be deflected upwards. So they will hit here. If the V3 is more and more, its value is more. Okay.
ओके सर.
So that was question number 36. Now we have question number 37. This we already have studied. A thermistor is connected in a circuit with a 6-volt cell, a 3000 ohm resistor, and a voltmeter. As shown, the graph shows how the resistance of the thermistor varies with the temperature. What is the temperature of the thermistor when the voltmeter reads 2 volt? You remember the potential divider? Uh, Here we have that circuit. This is R1, that is 3000 ohm. R2, I don't know, I want to know it. The V out is from the R2, across the R2. So the V out value is 2 volt, it is given here. The V out value is 2 volt. I will apply the formula, the famous formula of the potential divider. Let me show you that. Here we come. Here we go. Okay. So here we have, okay, this. So you can see that little bit smaller. I have to make it. Okay. Now you can see on your screen, this is the famous formula for the potential divider. If you take the V out from the R2, the formula is V out is equals to R2 divided by R1 plus R2 multiply the voltage of the battery. The R2 value I don't know. That's a thermistor. R2 I don't know what is its value. I will suppose it's X divided by R1 is 3000 plus R2 is X into voltage of the battery is 6. So you will cross multiply here. So we will have that 2 will multiply with 3000. It will give you 6000 plus 2x equals to 6 and x multiply 6x. And you will have 6x minus 2x, that will be 4x equals to 6000. That 4 will go on the other side, it will divide there. So x will be equals to 6000 divided by 4. That will be 1500 ohm. So the
ओके समझ
R2
आ गया.
value will be 1500 ohm. So the now I know the resistance of the thermistor. I know the resistance of the thermistor. So here we have a graph. Look at this graph carefully. Here the resistance is given of the thermistor, and here the temperature is given. So now I know the resistance of the thermistor is 1500. So here is the 1500 between 1000 and 2000. From here you come to this graph, okay? And when it cuts the graph, below that point, check what's the temperature. So that
60
temperature is
डिग्री.
how much? 60. So a very tricky question. This is the C looks the right answer to us. Question number 37, C looks the right answer, sir. Let me check. Question number 37, C is the right answer. Okay. Do you understand this?
Yes, sir.
Okay. Now, we are going to question number 38. You have not yet studied it. A radioactive source is placed 3 centimeter from a GM tube in air. The average count rate is 742 count. So radiation is coming out of some source, and we have GM tube. GM tube is used to detect the radiation. It will tell you the radiation is here and how much radiation is here. So whatever the reading comes on the GM2, we call it the count rate. So the GM tube, when you took the GM tube near the source, the GM tube gave you the reading 742. 742. Okay. Now what you did, you placed the radiation. First of all, the radiation is basically of three kinds. One is called alpha, the other one is called beta, the third one is called the gamma. So the radiation has three kinds: alpha, beta, and gamma. Alpha cannot pass through a paper. There is problem. We call it the penetration power. The alpha particles, they cannot pass through the paper. So if you place a paper between the source and the GM tube, the reading if drops, if by putting a paper between the source and the GM tube and the reading changes, it drops, it means the radiation has alpha particles. Why? Because the alpha particles cannot pass through the paper. So if you put a paper between the GM tube and the source and the reading drops, it means that the radiation has alpha particles. Okay. If you place and beta and gamma, they are not stopped by the paper. So if the beta and gamma is given out and you place a paper between the source and the GM tube, nothing will happen. The beta particles and the gamma rays, they are not stopped by the paper. So if you put a aluminum foil between the source and the GM tube, the detector, if you place a aluminum foil between the source and the detector, you see through the aluminum foil, alpha particles definitely they cannot pass through the paper. How come they pass through the aluminum foil? Beta particles can also not pass through the aluminum foil. So if you place a aluminum foil between the source and the GM tube and the reading drops, it means it has beta particles, because the beta particles cannot pass through the aluminum foil. But the gamma rays, they can pass through the, but they are not stopped by the aluminum foil, they are not stopped by the paper. The gamma rays can only be stopped by a thick lead sheet, a thick sheet of lead that can stop the gamma rays. Okay, so now try to understand what happened here. Then in the three experiments, measurements are taken with the sheets of different materials placed between the source and the tube. The results are recorded in the table. Material of the sheet between the source and the tube, thin card. He put a paper card, and the reading from 742 dropped to 273. Reading changed by putting a paper. It means the radiation has something which is stopped by the paper. It means it has alpha particles. So alpha particles are present in that radiation. Then he put the aluminum foil. The reading is still 275. By putting a paper, the reading became 273, and now by putting aluminum foil, it the reading is 275. It means it does not have beta particles because the reading has not changed. Then he put a thick lead sheet, and the reading changed from 275 to 68. It means it has gamma rays because they are stopped by the lead. So this radiation has alpha particles and gamma only. It does not have beta particles. A little tricky question. Question number 38. We think B is the choice. Question number 38. B is the right choice, sir. Okay, so we are moving to the next question. Question number 39 showing up on your screen. Which equation shows a nuclear fission reaction? You know, nuclear, there are two reactions, nuclear reaction. One is called fission and the other one is called fusion. In the fission reaction, what happens? A larger nucleus is broken down into smaller nuclei. You see, you take a larger nucleus, you bombard it with the neutrons, and that nucleus is broken, and smaller nuclei are formed. Okay, and with that, neutrons are formed. The famous example of the fission reaction is this, where the uranium is bombarded with a neutron, and the nucleus of the uranium is broken into the two smaller daughter nuclei, and with it further neutrons are produced. So D is the famous example of nuclear fission reaction. Fission reaction, there are two kinds of reaction. One is called fission reaction, another one is called fusion reaction. So here the example is asking for fission. They are asking you to give an example of fission reaction that happens in nuclear reactors, where a larger nucleus is bombarded with neutrons and it's broken down into smaller nuclei and smaller daughter nuclei, and lot of neutrons are also produced. So D looks the right answer to me, sir. Question number 39, D is the right answer. Yes, D is the right answer. So, question number 40 is showing up on your screen. Between 1909 and 1911, Geiger and Martin carried out experiments in which alpha particles were fired at metal foil. Most of the alpha particles passed through the foil with small deflections, but some were deflected through a large angle. These results suggest that, okay, these Geiger and Martin, they carried out experiments you must have studied in your chemistry. What they did, they took a gold foil, a very thin gold foil, and they bombarded alpha particles on it, and what they observed, that most of the alpha particles went straight through it, like nothing came in their path, but there was gold foil in their path, but the alpha particles went straight through the gold foil without any kind of deflection. Few of them were deflected at a larger angle. From this experiment, they came to know that the most of the space in the atom is empty, and only in the most of the atom is an empty space. There is nothing in it, and everything. But at the center of the atom, there is a nucleus, and that nucleus has all the mass, and it has positive charge. This was their finding by this experiment. He says atoms contain clouds of electrons through which some alpha particles cannot pass. That's not true. Atoms contain neutrons that alpha particles bounce off. Maybe. Alpha atoms have positive and negative charges spread throughout their volume. That's not true. Atoms have positive charges concentrated in a small volume. Yes, this is the conclusion they got. This is the conclusion they got. Sorry, everything everything turned into. Okay, so D is the right choice. D is the right choice. Geiger and Martin, by the experiment of bombarding a gold foil with the alpha particles, they concluded that the most of the atoms, most of the alpha particles went straight. So most of the space of the atom is empty. Only a small portion in the atom in the center has mass. It has positive charge. So D is the right choice. Question number 40. Look at the question number 40. D is the right choice. So, my dear students, today we have completed this paper. Let me show you the paper. Today we have worked on May-June 2005 MCQ paper, and I have done this paper in two parts. And this is the second part we are doing. and the subject we are studying is Physics 5054. Hope that you will, whenever you will be able to see this lesson, this will be very beneficial for you. So thank you very much, everybody, and it was a pleasure working with you. So thank you very much. Have a good day. God bless.